Why is the sky blue? The answer is stranger than you think. Every clear day, an enormous blue ceiling stretches above your head. It feels so ordinary that most of us never question it. But here's the strange part. If you left Earth and looked back from space, that blue sky would simply disappear. The sun would still be shining just as brightly, yet the sky around it would be completely black. So where does all that blue come from? If sunlight is white, why doesn't the whole sky look white too? And if the answer is hidden in the air around us, why can't we see it? The truth turns one of the most familiar sights on Earth into one of physics's most beautiful illusions. For thousands of years, people tried to explain the mystery. Some believed the sky reflected the oceans below. It sounds reasonable, after all, the sea often looks blue. But that idea quickly falls apart. The sky is just as blue over deserts, forests, and mountains, far from any ocean. Others imagined that air itself must be naturally blue, like tinted glass. Yet if you hold a jar of clean air, it looks perfectly transparent. Another popular belief is that the sun somehow shines blue light onto Earth during the day. But sunlight isn't blue at all. It's a blend of every visible color, from deep red to violet. None of these explanations solve the puzzle. Somehow, ordinary white sunlight enters a colorless atmosphere and creates a brilliant blue sky. The breakthrough came in the 19th century through the work of the British physicist Lord Rayleigh. His discovery revealed that the answer wasn't hiding in the light alone or in the atmosphere alone. It was hiding in the way they interact. Imagine sunlight as a crowd of tiny travelers, each carrying a different color. They all rush toward Earth together. Waiting for them is an atmosphere filled with countless invisible molecules, mostly nitrogen and oxygen. These molecules are unbelievably small, far smaller than the wavelengths of visible light. Yet every time sunlight passes through them, something remarkable happens. Instead of simply passing by untouched, some of the light is knocked off course. It scatters, bouncing away in different directions. But not every color behaves the same way. Colors with shorter wavelengths scatter much more easily than those with longer wavelengths. Blue light, with its relatively short wavelength, is scattered about 10 times more efficiently than red light. While much of the red light continues traveling almost straight from the sun, blue light is constantly redirected throughout the atmosphere. It spreads across the sky like countless tiny echoes of sunlight. That's why, no matter which direction you look, blue light is reaching your eyes. You're not seeing blue paint above you. You're seeing sunlight that has been scattered over and over again by trillions upon trillions of invisible air molecules. It's a beautiful trick of nature. The atmosphere isn't creating blue light. It isn't acting like a giant blue filter. It's simply redistributing part of the white sunlight that's already there. But this explanation leads to an even stranger question. If shorter wavelengths scatter more strongly, then violet should scatter even more than blue. So why isn't the sky violet? The answer lies partly inside your own eyes. Human vision isn't equally sensitive to every color. During daylight, our eyes respond much more strongly to blue than to violet. Even though violet light is scattered very efficiently, we simply don't detect it nearly as well. There's another piece to the puzzle too. High in the atmosphere, some violet light is absorbed before it ever reaches us. The combination of reduced violet light and the way our eyes process color shifts the balance toward blue. The sky isn't showing the most scattered color. It's showing the color produced by both physics and human perception working together. Once you understand that, another everyday mystery suddenly becomes much easier to explain. Why does the sky turn red every evening? When the sun is high overhead, sunlight travels through a relatively short layer of atmosphere before reaching you. Plenty of blue light is scattered across the sky, creating that familiar daytime color. At sunrise and sunset, everything changes. The sun sits low on the horizon, forcing its light to travel through far more atmosphere before arriving at your eyes. Along this much longer journey, most of the blue and violet light has already scattered away in other directions. What's left is dominated by the longer wavelengths, reds, oranges, and golds. The sunset isn't becoming red because the sun has changed color. It's becoming red because nearly all of the blue has already been scattered away before the sunlight reaches you. Weather can make the effect even more dramatic. Tiny water droplets, dust, smoke, or pollution introduce larger particles into the atmosphere. These scatter light differently from tiny molecules, sometimes producing hazy white skies or unusually vivid sunsets. The basic physics remains the same, but the details become richer as Earth's atmosphere changes day to day. The same invisible scattering also explains something you've probably noticed while hiking or traveling. Distant mountains often look slightly blue. The rocks themselves aren't blue. Between you and the mountains lies kilometers of atmosphere. Along that path, scattered blue light mixes with the view, giving distant landscapes their soft bluish appearance. Artists have used this effect for centuries to create depth in paintings long before anyone understood the science behind it. Now, imagine removing Earth's atmosphere completely. Stand on the moon at noon, and the sun blazes overhead with incredible brightness, yet the sky remains pitch black. That sounds impossible until you remember what creates our blue sky in the first place. Without air molecules, there is nothing to scatter sunlight across the sky. The light travels directly from the sun to your eyes, leaving the rest of the sky dark. That's exactly what astronauts experience in space. They can see the brilliant sun, the glowing Earth below, and endless blackness surrounding both of them at the same time. Our atmosphere doesn't just make breathing possible. It completely transforms the way the universe looks. Even more surprising, Earth isn't the only world with colorful skies. On Mars, the atmosphere is extremely thin and filled with fine reddish dust instead of Earth's mostly clear air. Those dust particles scatter light differently, giving Mars its butterscotch-colored daytime sky. And at sunset, something unexpected happens. Around the setting sun, the Martian sky can actually appear bluish, the opposite of what we experience on Earth. Different atmospheres create different skies. By studying how light scatters through distant planets, scientists can even investigate the atmospheres of planets orbiting other stars. Tiny changes in scattered light reveal clues about what gases surround those planets, bringing us one step closer to understanding places we may never visit. So the next time you look up on a clear afternoon, remember that you're not seeing a giant blue dome stretching over the world. You're watching an invisible conversation between sunlight and countless microscopic molecules surrounding our planet. Every second, trillions of tiny collisions redirect blue light across the sky, turning transparent air into one of nature's greatest visual illusions. That ordinary patch of blue above your head is far more than a beautiful backdrop. It's living evidence that light, matter, and even the limits of human vision work together to shape the world we experience.
And once you know that, every clear sky becomes something extraordinary, not painted above us, but created anew every moment by the invisible physics surrounding our world.